Theorem 1. Two intersecting planes meet in a straight line. Supposing we have two intersecting planes, M and N, and we have point A and point B lying in both planes. We have to prove that the intersection of the planes is a straight line. Point A and B, which lie in both planes M and N, determines a line by axiom 1, which says that if 2 points of a straight line lie in a plane, then the whole line lies in the plane. So, A and B lies in both plane M and plane N. So, line AB is the intersection of both planes M and N. By axiom 3, which states that two distinct planes cannot meet at one point only.
Theorem 2. A plane can be determined by a line and a point not on it, two intersecting lines, and two parallel lines. I have here a cube. We will use this one to prove the Theorem 2. With our plane R, we will determine if a plane should have a line and a point not on it. Now let C and D be the 2 points on line 1. Then 1 and 1 plane R can be passed through line 1 and point E, because 1 and only 1 plane can be passed through C, D, and E, and that is according to axiom 2, which states that through 3 non-collinear points, 1 and only 1 plane can be passed. Next, a plane can be determined by two intersecting lines. With our plane M, let C be the intersection point of the line 1 and the line 2, and D and E any other points, one on the line 1 and the other on the line 2. Then C, D, and E determine the plane M, in which lie in line 1 and line 2, and that is still according to the axiom 2. Lastly, a plane can be determined by two parallel lines. I have here the plane S, in which, by definition of the line 1 and line 2 lie in a plane S, they lie in only one such plane, since the points C and D on line 1 and E on line 2 lie in only one plane, and that is the Theorem 2.
3. If a line is perpendicular to each of two lines at their point of intersection, then it is parallel to the plane of these lines. We will be using this rectangular prism to prove our Theorem 3, but to have a closer look, we will use another plane to represent this side of the rectangular prism. Given line AP, which is perpendicular to each line 1 and line 2, we draw another line from point P, and we will name this line 3. Let Z be the plane of these lines. This line AP is perpendicular to line 3. Then, if it is perpendicular to line 3, AP will also be perpendicular to plane Z. Because according to axiom 71, which states that a line is to be perpendicular to a plane if it is perpendicular to every line in the plane passing through its foot, and point P is the foot of the line AP. In this case, the plane is perpendicular to the line.
Theorem 4. Through a point, there is one and only one plane perpendicular to a line. To prove that one, I have here an example. This is a rectangle, an example of plane. Assume that it is our plane N. Now, we have a given which is the point A, and with our line 1, we will put it to the point A. So this is now our example. Now, we will prove that Through A, there is one and only one plane perpendicular to this line 1. Now, we will use now a solid. This is a rectangular prism. Now, assume that this plane is part of this rectangular prism. Okay, so that you can picture it out. Now, once again, this is our plane N with our point A and with our line 1. Through A, we will draw lines AB and AB prime both perpendicular to line 1. So we assume that this will be our line AB and with our line AB prime. We use the B prime in order to determine that these two lines are having an equal distance. Then the plane M determined by AB and AB prime is perpendicular to line 1. And that is Theorem 4.
Theorem 5. Through a point, there is one and only one line perpendicular to a plane. Using this rectangular prism, we will try to prove Theorem 5. But for a closer look, we will use another plane to represent this side of the solid. Given plane S and point B, we have lines HB and AB here. If we put line HB here in point B, this line will be perpendicular to plane S. Assuming we put line AB here, this will no longer be perpendicular to plane S because this line is already oblique. And according to axiom 71, it states that a line is to be perpendicular to a plane if it is perpendicular to every line in the plane, passing through its foot. In this case, the planar is perpendicular to the line.
Theorem 6. Oblique lines from a point to a plane meeting the plane at equal distances from the foot of the perpendicular are equal, and conversely, two equal oblique lines from a point to a plane meet the plane at equal distances from the foot of the perpendicular. I have here a rectangular prism. We will use this one to prove the Theorem 6. Now, if you notice, we'll just only use the one plane. So we name this one as a plane F. And these three lines symbolizes that these are the oblique lines. And in order for us to prove this one, now try to look at the figure, the plane S. Okay. Now, given the QB is perpendicular to S and AB is equal to CB. Now, to prove that QA is equal to QC, we will use a distance formula. Now, I have here a Cartesian coordinate plane. We will use this one to prove the distance formula. So, like what I have mentioned, that we must have to prove that QA is equal to QC. Now, given already that AB is equal to BC, we assume that the value for letter A will be negative 4 and 0. For letter B, 0, 0. For letter C, 4, 0. And for our Q, that would be 0 and 7. Now, the distance formula would be square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. First thing, we must have to prove first that AB is equal to BC by using the formula. First, for our line AB, we have the square root of negative 4 minus 0 squared plus 0 minus 0 squared. So, that would arrive with the answer 4. Now, let's proceed with our line BC. For our line BC, we have the square root of 4 minus 0 squared plus 0 minus 0 squared. And still, it would arrive with a value of 4. So, it means that line AB and line BC is equal. Okay, now let's prove that QA
is equal to QC by still using the distance formula. Okay, for our QA, we have the square root of 0 minus negative 4 squared plus 7 minus 0 squared. And that would come up with the value of square root of 65. Next, for our QC. Okay, for the QC, we have the square root of 0 minus 4 squared plus 7 minus 0 squared. And we would arrive with a value of square root of 65. And that would be them true that the theorem 6 have been proven. So, QA and QC is equal to each other. Thank you for watching.